Last night, like it's last night. If the world was ending, I wanna be next to you. Hello there, everyone, and welcome again to another stream here on Freaky Physics. And today we're gonna do some physics. Specifically, we're gonna do some stellar evolution, and then we're gonna try to get into thermodynamics. All right. So with that, let's get into the classroom. See, we're already here. Oh, not yet. Let's just wait a bit. Yeah. I think I'll do something soon. I think I'll put the cable here for the internet. I'm dropping a lot of frames right now, I think. Yeah, I'm losing 10% of my frames. Doesn't sound like much, but that's gonna make it look jumpy, right? Especially at 60 frames per second. Yep, I'm streaming at 60 frames per second, I think. Alright, now that I mentioned it, look, my internet connection just got stable. Alright, but anyway, while we are waiting, let's take a look. It's already 8 o'clock. Yep, everything's connected. Oh, here we are. We have some problems up here. We're gonna start real soon. Okay. Right, I also just received a couple of problems. And here we go. Let's start. Hi, Gita. Good.
Oh.
Weeks. The reason I was away, we at that day we went traveling because it was like a 5-day holiday here. So,
Oh, yeah, that's reasonable.
yeah, and the day that we were supposed to have a lesson, that's when the trip started. So, all right. So anyway,
Okay.
all right. So, yeah, you sent me over a couple of pictures here for questions you wanted to ask. All right.
Yeah.
Okay, so which one should we start with? Oh, um, by the way, before we do start, I just gotta ask you, or I gotta tell you something. Uh,
Mhm.
you have You watch Netflix, right?
From time to
Time
time.
to time, right? Uh,
Yeah.
yeah. The reason why I asked is because yesterday my wife decided to watch something, and I looked into the TV what she was watching. She was watching Geek Girl, and the lead actress reminded me of you.
Oh. Sorry, what was the name of the show?
Geek Girl.
Geek Girl.
Yeah,
I haven't heard of
yeah.
it.
Well, there are you do have similarities. That's all I gotta say about that. All right. So,
I'll have a look.
all right. What was I gonna do now? All right. Let's go to. All right. Let's go here. All right. So let's take a look at the first question you have. I guess we'll do the questions about stellar evolution first. Which one
Okay.
is it gonna be? That's pressure, electron. Okay, and you also sent over a couple of questions about photons.
Yes.
Okay, right. Which one should we start with? Definitely not that. Not that. Uh, okay, let's do this first. Oh, it's the same one. Is it? No, not exactly.
Mm. The reason
Ah.
I didn't send many questions
Mm-hmm.
um was because I wanted to go over theory, but I don't know if that's a bit unstructured then.
Actually, if you want to go through theory, we can go through that first, and then we can go through the questions.
That would be really useful.
All right, so let's go over the theory first. Let's go through your questions first again. All right, the first one: why does luminosity and radius peak twice in the life cycle in the star? Right? Oh, that's easy.
Hmm.
But let's start with that. Okay, so let's go back to stellar evolution, and this time around, I'm not gonna draw it. I'll just take an image from the internet, just to make it faster.
Okay.
Okay, evolution diagram. Okay, and which one looks nice? This always looks nice. I always use this particular image. So this is how stellar evolution basically goes. Okay. Um. Here we go. All right. So that's how
Okay.
it goes. The idea here, before we go into your questions, um, is that whenever you have stars, they will all, well, most of them, not practic. I'm gonna say that most of them. I can't really say it for every single star, right? But they're practically gonna evolve in one of three ways, two of which start off similarly. Okay, so this is step one. This is the first step here. This is, and I'm gonna do something like that here. This is the second. This is the second part, and this is the third possible path. Okay. Now, the reason why this happens is because here on the nebula, when this starts, this initially just starts off as regular gas. Yeah, regular gas and dust. Okay,
Yeah.
so if it's just regular gas and dust, do you expect it to actually glow?
No.
No, right? It can get warm, but it's not gonna glow, right? Now, what happens here in at this stage, and I'm gonna use orange here. At this particular stage, though, something happens. Whether it's a low or medium mass star or it's a high mass star, this particular stage, happens when there is sufficient mass to for hydrogen atoms or nuclei. Let's use the word nuclei to sufficient mass for hydrogen nuclei to collide fast enough.
Hmm.
Okay, to start fusion reactions. if your star does not meet that particular mass, we know what this sufficient mass. We have a term for this. This is the Jean's mass. Okay. If the mass of the nebula is below the Jean's mass, fusion cannot occur. Once it reaches the Jean mass or slightly bigger than that, by slightly I mean up to about 100 times the mass of the sun. Okay, as long as it's got
Whoa.
sufficient mass, uh, it goes beyond the Jean's mass. The gravity is going to be strong enough to pull the hydrogen together, and at the same time, the hydrogen will, once they collide, they don't bounce off each other anymore. They just undergo fusion. And in this case, this is your first um this is your first um spike in intensity. I'll just write first intensity spike, okay?
Why?
Why? Because what happens here is the fusion, when it starts, that's when it starts glowing. So imagine this, you just have a gas cloud, and then all of a sudden fusion starts. A lot of energy suddenly released. And then, because suddenly
Yeah.
released, it starts glowing.
Okay.
All right? So, where does the second spike occur? Right, just luminosity. Okay, so in other words, the luminosity spikes here the first time. Okay, the second time that it spikes is where? The second
Mm.
part where it spikes is here for most stars. Sometimes it this is the second time.
So right after.
In other words, when it turns into a giant. Okay, why? The reason here, let's just put it here. This is the second luminosity spike. Luminosity spike. Okay, the reason why that happens is, well, at this point, let's just write down what's happening here. On the first part, hydrogen uh, undergoes fusion. Okay, here on the second part, your hydrogen starts running out, and then it's gonna get into the point we're in. It's gonna start burning helium. Okay, all
Mm-hmm.
right. Now at this point, let's go to the first part again. This hydrogen turns into helium, right? And then this helium, um, on the second part on the giant phase, this turns into heavier elements. Heavy elements. Okay. Now, what is heavy? Go ahead. You have a question.
Sorry, under what process?
Okay, this is still fusion. Both of these, in the main
Uh-huh.
sequence and the red giant, they're both fusion. But in the main
Okay.
sequence, it's hydrogen being fused. In the giant stages, helium is being fused. Okay.
Okay.
Now, the third one, and this is not true for all of them, it's just true for high mass stars. This is the third part. Supernova, right? This is your third luminosity spike.
Mhm.
Now, I think you can understand why this is the third luminosity spike.
Because it's really bright.
Yeah, and why is it very bright? It basically just because it explodes, right?
Yeah.
All right. In that explosion, there's no more helium being fused, and in this case, there's no more fusion in the first, no more fusion at all. It's just really the energy in the star is released all at once because of the explosion. Okay.
Hmm.
All right. So again, let's just note that here for high mass, high mass stars only. Okay.
Yeah. And sorry, what happens that it explodes?
Oh, oh, why? I think it's better to ask here. Why does it explode? Okay.
Yeah.
All right. So, let's go here, and I'll just take an image from the internet. Supernova explosion stages. Image. Where is a good one? All right. Actually, here's a good one. This is actually right. So anyway, for the purposes of the stream, for those who are watching, yes, I will not I will not say that there are sources, but there are sources. Okay. Anyway, here's the image. There we go. There are two types of supernovas, generally speaking. Okay. The first type, um, okay, this type one supernova. This is for white dwarfs. Okay. So we will go to how this works later. Okay. What we're what we're gonna focus on is a type two supernova. Okay. Now, the type two supernova happens. This is for um giants and supergiants. Okay. Now, what happens here is once your core starts having helium, it starts producing all these heavy elements like so. So let's focus here, right? And in the core on the iron, later on, eventually, iron gets produced because of all that fusion. Fusion still occurs until we get to iron. Now, do you remember this diagram? Let me check it out. Diagram. Uh, diagram. Okay, here we go. Do you remember this diagram? Let's get a good one. This is gonna work. All right. Okay, there we go. You remember this diagram from nuclear physics?
Yeah, yes.
Okay, and we've also talked about this diagram, this feature of the diagram, that iron is here, right?
Yeah.
Okay, so what does this mean? This means the let's just go to the short way. This means this is very stable and
Highest binding.
yeah, highest binding energy per nucleon, and therefore not um okay. To be more specific, I'll say it this way: fusion and fission um need need energy input. Now, most of the time when we say fusion and fission, there's an energy output, right? But for
Mhm.
iron, you have to send energy into the nuclei for them to fuse. They will not spontaneously fuse. They will not spontaneously split apart. Okay? Now, so imagine this now. Because of this heavy iron core in the middle of the star, it's now very stable. It's not going to do fusion. It's not going to do fission. So what's going to happen? There's no more energy being produced, right?
Could it not take energy from the heat?
Well, it could. But remember, the idea here is even if it does, let's think about it in terms of temperature to make it a bit easier to imagine, okay? So when hydrogen undergoes fusion, when they come together, they end up being hotter, so to speak, right? So the helium moves faster than either the hydrogen atoms, so to speak. There's
Hmm.
energy released, right? But iron, because it takes in energy as it fuses, it kind of cools down the whole thing. It cools down the whole star. And
Okay.
and in that process, because it's taking the iron is going to take energy to fuse. So when they do fuse, again, most of the time it won't. Okay, but when they do fuse, it's going to take even more energy from the star. It's gonna make the star cooler, and once it's cooler, what happens? What happens here? The let's use yellow again. Here, the core cools down. Core
Mm,
cools down a bit, right? But
yeah.
more importantly, aside from just cooling down, it is no it doesn't produce no more heat. I'm going to focus on the heat first produced, okay? Because there's no more heat produced, is there enough energy to actually battle with the gravity? Because here what's happening here is the all that energy. from the fusion is so like that. Fusion rather. Fusion counteracts gravity, right? So to be specific,
Yeah.
energy from fission, from fusion, okay? Gravity. But because here, there's no more energy to counteract gravity, right?
Yeah.
No more energy to oppose gravity. Okay. Now, the idea here now is that the core is made of heavy iron. The outermost layers here, they're more they're composed of lighter hydrogen atoms and other atoms as well, or other nuclei, right? Now, I
Mhm.
would really love to do this here with a real demo, but I don't have the space to do it. So
Mhm.
I'm just gonna ask
It's
you
okay.
this. I'm just gonna ask you to do this. Imagine you are running towards a truck with the intent of bumping into it as hard as you can, and then you do so,
It's a
right?
truck. Mhm.
It's a truck. Let's just say that the truck is not moving.
Okay.
So you're safe. It's not gonna. You're gonna hurt yourself, but you're not gonna end up dead. Okay.
Okay.
But yeah, you're running full speed into the truck. The truck isn't moving, and then you bounce off the truck. What happens?
Yeah.
What actually happens when you collide with the truck? Then, you're gonna bounce off, but does the truck actually move?
No.
It barely moves. If you really want to think about it, it will barely move, right? So
Yeah.
it's the same idea happening here. The hydrogen nuclei are so tiny compared to the iron nuclei that when they collide, what bounces off?
The hydrogen.
The hydrogen. So in other words, what's happening here? Let's just do it here. This is the iron, right? And then the hydrogen goes in there, comes in. That's a bad choice. Okay, there. This is the hydrogen, and because again, hydrogen is so much lighter than iron, that the hydrogen bounces off. And that's how the explosion happens. It initially starts with all that hydrogen actually falling under the influence of gravity and then bouncing off the iron, then going kaboom. Okay.
Oh.
Now, in case you're wondering why does it explode instead of just oscillating, basically there's still a lot of energy stuck in there in the star. Part of it is the hydrogen going bouncing off the helium. Some of the iron rather. Some of that hydrogen will again fuse on that particular part, providing a little bit boost of energy to make the star explode.
But do the hydrogen particles make pressure in the core or
They do actually, but that actually compresses the core to a certain size, at least until the supernova is done exploding. All right, but what does this mean? What does this mean? So eventually, you're left with a core. This is your core, right? And we're not gonna refer to it as an iron core. We'll just call it a core. And then the rest of the star has now scattered around. Okay. Now, all right. Does that make sense?
so this image is when a supernova is of
Yeah.
a supernova?
Yes. The other
Okay.
supernova here is for type 1 supernovas, which you will, if I'm not mistaken, you will also learn, but for a different context. Okay. This other one is
Okay.
more for how stars actually evolve over time.
Okay. So the bouncing of hydrogen
And all the other
makes
lighter
it,
atoms, yes.
yeah, it makes it more unstable, then it collapses under
Mm-hmm.
gravity.
Yeah. So again,
Okay.
the iron core doesn't provide energy anymore to oppose gravity. So the lighter nuclei come in, collide with the iron core, bounce off, form supernova.
Okay.
All right. Okay. Um. So last thing about this, in case you are still interested in this part. Okay. So we have that the rest of the thing coming out, right? This core, obviously, this core will have a mass that is smaller than the star. its source star,
Mhm.
right? So in other words, we do not count. So once we have the supernova, we don't count the mass of the star. We only count the mass of this core. Okay. Now, there is another limit that we have to look at. This actually mentioned again in part of your astrophysics lessons, but we have what we call the um, TOV limit. Okay, TOV here stands for the three scientists who came up with this idea. Okay, the TOV limit is approximately 10 solar masses. Okay, so again, you will count in this case the core mass. Okay, the core mass is less as approximately 10 solar masses. If the core
Okay.
mass is less than the TOV limit, okay, limit, um, what do you get here? Most of the time, you'll get a neutron star.
Mm-hmm.
Okay, all right. So again, neutron star. Now, if the core remnant, if the core mass is greater than the TOV limit, I put limit here. Okay, if the core mass is is greater than, actually it should be the other way around, isn't it? So it should be like that. So core mass is smaller here, core mass is larger here. You get a black hole. Okay, black holes. So the reason for that, it's not because of the stellar evolution anymore. It's now about general relativity, which you will only get a feel off later on. You're not gonna go in very deep into general relativity. Okay.
Okay.
All right.
Yes.
Okay. So, all right. Does this make sense now? Why that happens?
Yes.
Right.
But I do also have a question.
Mm-hmm.
Um, regarding, I think I sent a graph last time. It was the graph of the surface temperature with luminosity of the
Yes.
stars.
Yes. I'm looking
Um,
at it right. I'm looking for it right now.
okay.
Is it?
And I don't really understand why it's drawn like that.
Yeah. You're talking about the Hertzsprung-Russell diagram, right?
Yes.
Okay.
Yes.
Now, here's the idea. Let me just copy what you sent over. Okay.
Because we use this to follow along the life of a star,
Yep.
but then there's these blocks that are separated off.
Copy image. All right, here we go. So since we are gonna go there to the Hertzsprung-Russell diagram, it helps to realize something here. Okay. First of all, I'm gonna ask you something just to make it make a lot more sense, because I know, yeah, this doesn't make sense if you don't get this particular aspect. Okay. So I'm gonna ask you first. You have a piece of coal.
Okay.
Okay. And that piece of coal is burning as hot as it could. So it's like glowing really,
Mhm.
really brightly, right? But what you do is, once you get it burning, you like, let's say that you have like a big block, like the size of I don't know, a Rubik's cube. Let's just say it like that. They have the size of a Rubik's cube. Okay. And then
Mhm.
imagine you're gonna take off, somehow you can do it. You're gonna take off one of those smaller pieces from the Rubik's cube, but it's still glowing, right? So you can see.
Yeah.
So what you can do here is, I will continue working it here. So I'm gonna draw it here first. Yeah. So you have your, that's your lump of coal glowing, right?
Cool.
Okay. And then let's say that you have another smaller lump of coal burning at the exact same temperature. So they're so equal temperatures, right? Let's use black.
Yeah.
Equal temperatures. Okay. So, um, so what's the only difference between these two? This is smaller, right? Now we're gonna
Yes.
say smaller area. We're gonna focus on the surface area here. This is a larger surface area. Okay, area. Now the question now is between these two, which one? What can you say about the peak wavelength? In other words, the color. They should be the same, right?
Yeah.
Okay, but which one's brighter? Blank is brighter from afar. Let's do it from afar.
The bigger one.
Why is the bigger one brighter?
Because it's proportional, like luminosity is proportional to the area.
Exactly, right? Or that's the way we would say it in a more technical way, right? Luminosity is proportional to area. Luminosity is proportional to area, right? And then here the peak wavelength is the same because in what's this? The intensity is the same, right?
Yeah.
Okay, luminosity is proportional to area, and also intensity, right? Okay, intensity like that. But we're focusing on area. So I'm gonna change it from the word coal to the word star. It should the exact same thing should still work, right?
Yeah.
Okay, so this explains part of your Hertzsprung-Russell diagram. So let's go back to the actual diagram here. Yeah. Okay. Um, without looking here at the temperature first, we're only focusing on the luminosity bit here. Okay, luminosity again increases with area, and therefore let's also say that this let's write it here, luminosity, I'm not going to say proportional now, but increases with radius, right?
Yeah.
Right, so let's go back to the diagram again. Since luminosity increases with radius, what's happening here? When you go up the y-axis, which is luminosity, you're increasing the radius of the star.
Yeah.
That makes sense now, right? So you can see here why the ones here lower here would be white dwarfs, and the ones up here would be like either main sequence or giants, right? Okay, so that makes sense
Yeah.
in terms of size, right? Now, the
Yeah.
other part here is this, the color. Now, we just use different codes here, O, B, A, F, G, and then we kind of don't really draw this to proper scale, right? I think this is a logarithmic scale. But anyway, the idea here is, according to this scale, this is temperature. This goes back to our first part. Actually, we'll do a second bit, okay? So let's now do two bits of, now let's do two stars now. But we're still going to imagine them like coals, okay? So here, you have your two stars. This is going to be hotter. Let's turn it blue. This one. Oh no, this one. Okay, let's turn this one star blue and that other star red, right? So which one is hotter?
The blue one.
The blue one is hotter. Why? This is temperature to the 4 is proportional to um peak wavelength, right? So this is the cooler.
Yeah.
Cooler. The idea here, by the way, is because um blue wavelength is, hold on, something's off here. Is it? Oh, okay. Temperature is proportional to wavelength. The shorter the wavelength, the word. Okay, or the 1/. Okay, I think that should be it. Okay. Oh yeah, this is it. Okay,
Okay.
is lower, so hotter, right? Okay. All right. So that's the relationship. Now, what's gonna happen here because of this fact? Um, we're so O stars in the diagram are hotter. Okay. So if we go back to our Hertzsprung-Russell diagram, again, we'll ignore. Oh, by the way, before we go to hotter, which one looks brighter? Which one is more luminous?
Uh, the blue one?
So blue is more luminous, right?
Yeah.
Okay, right. So because blue is more luminous, let's go back now to the Hertzsprung-Russell diagram. We will again ignore for now the luminosity here. Okay, and we'll put here in the temperature. Now, for something, what we'll do now is we will actually compare stars that are more or less the same size here. Okay, they're more or less the same size, but look at their colors for the most part. Okay, so most of the stars here though, at the lower end, are either here on the red end or they would be here on this area. There is nothing basically in between, right? Similarly, when we go to the higher luminosities, the bigger radius stars, it's basically the same thing. They have the same size, but they all have the same size, but yeah, they all have the same size. But what's gonna happen here is once you put all the stars in, most of these stars happen to go on this band. That's why it's called the main sequence, because most of the stars are here.
Yep.
Okay, now let's take a look at what giants do. Super giants. So if we look here, super giants are bright stars, but generally cold. And for them to be cold and bright, they have to be huge. Okay. Now,
Okay.
similarly here on main sequence, most main sequence stars, they are hot and bright. They don't have to be as big as the super giants. Okay. Now, similarly here for these white dwarfs, they are hot. They're hotter than these main sequence stars here, but they are also so between these two, the white dwarfs and these stars here, which ones would be smaller? The white dwarfs would be smaller than these stars here.
White dwarf.
Sorry, say that again, please.
The white
Mm-hmm.
white dwarf.
Yeah. All right, true. So the white dwarfs again would be smaller because
Sorry, you meant
between the white dwarfs here, let me highlight that. Between these guys, the white dwarfs, and this part of the main sequence. Let's do that part. So, what would be,
yeah.
which ones, they're equal
I'll say
brightness,
white dwarf.
but white dwarfs are hotter. So for them to be hotter and as bright, they can be
Smaller.
smaller than the main sequence
Okay.
stars, right? So you understand how to read this now?
Yes.
Okay. So let's take a look. Why are giants here?
Because they're hotter.
They're
No, they're more luminous because they're bigger,
they're
but they're the
luminous
same
because they're
temperature.
big. Correct. They're luminous because they're big compared to what? Compared to the main sequence. All right. Now remember, just one thing for you to help remember this. When you're saying big and small, we're always comparing big and small stars to main sequence stars. These main sequence stars are more or less the same size. They're
Okay.
they're like within one one order of magnitude, I think, or two orders of magnitude. So basically, what am I saying? These stars are around 100 times as big in diameter as these stars here. And in the grand scheme of things, 100 is not really that big, right? Considering the scales we go to with stuff in the universe.
Okay.
Okay, right. That makes sense now, hopefully. All
Yes.
right. So okay. So again, today, let's just go to theoretical stuff. Okay, let's go to your next question that you sent over. Let me see. Let me see. Luminosity, radius. Then the radius. Why does it peak? Oh.
Oh yeah, why does the star? Because we did a simulation and it went back and forth. The radius
Mm-hmm.
peaked. Nice.
Okay, the first peak is definitely when it goes. Okay, is that gonna be the first or the second peak? So let's go back here to that diagram here. This one, right? So you can see where one peak happens from main sequence to giant. Okay.
Yeah.
Now, the reason why it peaks like that is because again of the fact that it has to burn hotter for helium to fuse. We're using the word burn
Right.
here to mean fuse, okay? To have just a temperature, okay? So it
Mhm.
has to burn hotter so that helium can fuse. And in order for the star to burn hotter, that means it's outputting some amount of energy that's bigger than before. So the fusion energy is at this point or at the beginning of the red giant phase, it's going to be stronger than gravity. So it's going to expand until it stabilizes. Okay? So
Okay.
that's
Yeah.
okay. I cannot imagine where the second one or where the first one comes, where the radius would increase. Oh, okay. I think I see. It's gonna be here as well on the path from nebula to main sequence. Okay, for the same reason. Once the hydrogen starts burning, once it starts fusing, it's gonna start off small, and then the hydrogen fuses, and then it's going to expand because initially the fusion is stronger than gravity again. But this time it's the hydrogen fusion that's stronger until again it stabilizes in size. At which point,
Okay.
either case, in both cases, when it stabilizes, that means the fusion energy has perfectly balanced the gravitational pull.
Okay.
All right. So they both coincide with the intensity spikes or the luminosity spikes. Okay. Think about it. Even the supernova is kind of similar. The supernova, the radius suddenly increases because it explodes, right?
And but do we measure the radius of the core, or just the whole star?
No, we don't have to do that for the supernova anymore.
So we measure the whole radius.
Yeah.
Oh,
All right.
okay.
So okay. Now, what's the next question? Thermodynamic processes where you have graphs for. Oh, okay. I'll be honest with you.
Mm-hmm.
Even when I was studying this took me like a whole semester to partially understand. I still don't totally understand this. I kind of, by understand, I mean I can't remember it from the top of my head. I really need to look at diagrams and stuff, okay? But there are a few
Okay, that's
shortcuts. There are a few shortcuts for you to help remember this, okay? But
okay.
first, let's roll down here now. Uh-huh. And let me get.
We can even do. Sorry.
Okay, I'm just gonna actually get an image again. Yeah, let's start with which one? Let's thermodynamic. Okay, let's start with the. Let's do the Carnot cycle. Okay,
Mm-hmm.
cycle diagram. Now, in this case, oh, let's. Which one am I gonna take? Okay, let's take a basic graph like this first. Okay, so the basic graph is basically just a rectangle with. Oh no, not a rectangle. Something like this. Okay, I know. Thermodynamic. Okay, let's use a more simple one. Okay, I think this is gonna work. Okay, calculating work done. Okay, so I'm gonna do two things: isobaric, isothermal, and adiabatic. I'll just put them here like so. Okay, you have the fourth one, isochoric. That's bar is pressure, thermal is heat, so choric would be volume. Okay. All right.
Okay.
The reason why I don't usually see isochoric is because isochoric processes are relatively boring. Okay, now let's start with ISO. Let's start off before we even go to these graphs, because these are the three basic graphs that we can work with. Yeah, before we start here, remember this: work done equals force times distance, right?
Yeah.
Now, if you think about this, now I'm gonna this time around, I'm just gonna draw the most simple case that we can think of for these problems, where you have a cylinder with a piston inside, right?
Yeah.
Okay, so again, these are usually the more simple cases. Now, if you think about this, in this case, this has a constant, this has a set radius usually, right? And then it's got a set height wherein it can change. And let's just say that there's gonna be h1, and then eventually there's gonna be, it's gonna come up here, it's gonna come to a second height h2, right? And therefore this part is delta h, the difference in height. Okay,
Yeah.
all right. Now if you think about this, let's think about volume. In this case, the volume, in fact, I'm not even gonna change this to r. Let's just say that this has a cross-sectional area a. Okay, the volume here will be equal to a times whatever height we're dealing with, whether it's h1 or h2 or delta h, right? So keep this
Yeah.
in mind. Now also, one more thing, you know that the piston is going to move up and down. So
Right.
the main idea here that I'm going to try to get to is this: the area is constant, right? So in other words, the volume is proportional to the height. Okay, okay. Now that we have established this particular fact, let's go back to the formula for work done. In this case, if there's gas here and it's going to, so let's say that the gas does work, that means delta H changes. Delta H is not equal to zero. That's what it means, right?
Yeah.
So also this means, conversely, this also means if delta H equals zero, there is no work done. Again, that's pretty obvious when we look at the equations and everything, right? How
Yes.
do we translate that into the graphs? That's the problem now. Yeah. Okay. So
Yeah.
let's start with the isobaric process. Okay. Let's start from points 1 to 2. In this particular case, what does this mean? Point 1 to 2 means your pressure increases, P goes up, volume, no change, right? Okay, that's from 1 to 2. And then here from 2
That
to 3, let's do it like this.
sorry. When does it happen that the pressure increases without the volume changing?
Okay, volume, no change. Now, okay, let's go back to ideal gas loss. If the volume doesn't change, but the pressure increases, what did you just do? So this also
Oh,
means
temperature.
the temperature also increased. In other words, if you um, increase the temperature, then this also means heat is supplied, right?
Yeah.
So, in other words, in an isobaric process, step 1 to 2, you supply heat to the system so that the temperature of the gas increases, but the pressure increases with it, but the volume doesn't change. Okay, but going back to what we said, if the I think I missed one particular aspect here, so I'll go back here real quick. So let's just do it here briefly. If delta H equals 0, then that means delta V is also 0, right? So what does this mean? If delta V equals 0, no work done.
Okay.
Okay, so in other words, here from 1 to 2, you don't do work, no work done. It's only that the temperature increases. So work done equals 0 from 1 to 2. All right. So going
Yeah.
back to the isothermic, let's go now to the isothermal graph. Where do we see something similar to that?
Mm,
So
I have
here,
no idea.
again, think about it this way. Pressure increases, volume stays the same, no work done. So that's the first one. P changes, V is not changes, then no work, right? Okay.
Yeah.
So here in the isothermal graph, where do you have no work done? So on the graph, what does that look like?
1 to 2.
1 to 2. In other words, vertical line. Okay.
Yeah.
Okay. So we'll do the adiabatic system later, but here we have work done equals 0. Okay, on 1 to 2. So let's go back to the isobaric system because that's the one easiest to see, right? Now, here in 2 to 3, let's focus on 2 to 3. How much work is done here? The pressure stays the same. That makes it
Uh,
easier to look at. We just need to take a look at the V, right? Okay.
yeah.
So in this case, pressure is constant, volume increases, right? So in other words, okay, let's
Temp.
let's let's put that heat is supplied, right? Heat is
Yeah.
supplied here and there. So what happens here? Work done, not equal to 0, right?
Yeah.
Okay. Now, it just so happens. Let's take a look at the unit for pressure. Pressure is gonna be newtons per square meter. I'm gonna do it the old-fashioned way, right? And then volume is equal to meter cubed. This in terms of the what's this? In terms of the units. So what is PV? Again, just looking at the units, what's PV? PV is
And
N meter, Newton meter,
um.
right? Meter cube over meter squared. That cancels out. You're left with Newton meter. Now, that looks awfully familiar, doesn't it?
Yeah.
What's that? That's work done,
Um. Yeah.
right? So, in other words, PV is work done. Okay? And in fact, we're gonna just do that. Let's lock this. Okay. So I'm not gonna say work equals 0. I'm gonna say now that work equals PV. Okay. To be more specific, I'm not even gonna say PV, but P delta V. Okay. So in other words, if from 2 to 3, and I'm gonna do it here, that's the area here, right? You see that
Yeah.
area? Okay, so that's gonna be clear. Okay. So I'll undo that real quick. Now, how about 3, 4? What's the work done here?
Um. Also, just volume decreases, so it's PV.
Okay, no, the volume doesn't decrease in 3, 4.
So the pressure
It's
decreases,
only the
so
pressure.
temperature.
Yeah. So in this case, the heat is removed, the temperature goes down, and then the pressure goes down. So, but the work here is equal to 0, right? No, 3, 4. Because again,
Volume doesn't change.
volume doesn't change. Now, how about here from 4 to 1? Going back from 4 to 1. Let's do this shortcut now. What's the work done in this part? That's going to be um I'm gonna call this V2. No, actually never mind. Okay. Uh let's remove that. Let's just say V2 for now. PV2, right? What's the work done here on 4 to 1? This is gonna be pressure 2.
PV.
Okay, pressure 2, V2. This is gonna be pressure 1, volume 1, right? Okay, which if you think about it is this area right here, right? Okay, so we can now see that from looking at the isobaric process, It's always gonna work, but the isobaric process actually makes it really obvious. So what's the total work done?
Of the whole
Mm-hmm. This will be equal to the
area.
area, the big area, right? Minus small area, right?
Yeah.
Which basically gives you the area of the shape. Area of the shape. Okay. So in other words, if we look here, I'm just gonna shade it now. This part up to here only, this is the work done. Okay. Now, now that we've seen it in the isobaric system, we can use the same idea to look at the isothermal system. In the isothermal system, what's the work done? It's gonna be
The area.
just this area again. Okay, that's the work done. Okay, and finally, the same thing with the adiabatic process. It's gonna be, this is again the work done. Okay, okay, I think I'll do one more thing before we end for today. Just one quick thing. Now, look at the isothermal and the adiabatic processes. Where do we get more work done? An adiabat, um, otherwise identical adiabatic or isothermal systems?
Isothermal.
Isothermal. Now, last thing now, what does isothermal mean? We keep the temperature constant, okay?
Constant.
So constant temperature. Let's do it here. Constant temperature. This is the part that I would always struggle with. Isothermal's easy. Um,
Mm-hmm.
Isobaric's also easy. Isochoric's also relatively easy. Adiabatic's the one I struggled with. Okay, but
Well,
the way
yeah.
I figured it out to make it easier to do so is I'll just say what it does first. This is no heat um input or output. Okay. Okay, so in other words, when you change the temperature of a gas, you can keep the, or rather, when you change the volume of a gas, but you keep the temperature constant, you're still putting in energy. Okay, but in an adiabatic system, what would happen is, um, it happens so fast that you can consider that nothing comes in, nothing comes out. All the work done is because of the gas itself doing the work. Okay, now, uh, the reason I kind of made it, I found an easier way to see it is I just figured something out. A in Latin means, is it Latin or Greek? But either one, no or none, right?
Uh-huh.
Okay. What does diab here? Diab here actually has the same root as the word diabetes.
Mm-hmm.
Okay. Now, the diab part here means going through or passing through. So in other words, when there's no heat input or no heat output, no heat passes through the system.
All right.
Okay. All right. Okay. So these are three of the four diagrams you asked for. We can go through the isochoric graph tomorrow. Okay.
Okay. And I'll get some questions
Yep.
and from today.
Yep. All right. Okay.
Okay.
So
Perfect.
we'll continue tomorrow at what time? 9 o'clock here. Right.
Okay.
All right. So okay. So you have a good evening. Is it evening already there?
Have a good not yet.
Not
It's
yet. All
3
right.
p.m.
All right. So I'll see you tomorrow either way, and you have a good day. Okay. I'll see you. Bye bye.
Yes. Have a good day. Bye
Bye bye
bye.
now. Right. So there we go. We'll end it there. We'll end the stream there. Did anyone go online? Not really. But yeah, it's fine. Right. And what actually happened here? Ooh, what happened to my board? Huh. What happened there? What did this do? Oh, my MS Paint. Okay. Alright. Well, for in that case, yeah, I didn't notice that. But, oh well. I'll always redo some of these videos anyway, so it's fine. But yeah, going live's always a good idea. But yeah, here we go. That's basically it. Um, so yeah, for thermodynamic cycles and stellar evolution, that's how it happens. Okay. So at this point we can end the stream. So before we do, don't forget to like. Where did that go? There we go. Don't forget to like, share, and subscribe to the channel. We are on YouTube, Facebook, TikTok, Instagram, and on Twitch. Yes, TikTok's still alive. So yes, follow us there. Um, so with that, we'll end here. So I wish you all a good morning, good day, good evening, good afternoon, good night, wherever you are in the world, and stay freaky, everybody. Bye bye now.